Today we study C20. This PDF file for completing the square and quadratic equation can be downloaded freely from kpop.org. If you visit kpop.org, then you will find table of contents. You can click this Escape from Scientific Absurdity Series C. Then you will find C20 here. And if you click this button, this PDF file can be downloaded. And if you click this one, the Korean version of the lecture is available. And now I'm recording the English version. If you click this, then you will return to the kpop.org page. And then if you click this, you will find our YouTube homepage of K-pop. Okay, so here there are the various playlists, and if you're interested, look around at this K-pop YouTube homepage. Okay, let's begin with the C20. Today we study the completing the square. Perhaps most of you are very familiar in middle school. First of all, we discussed the translational invariance of the Euclidean space. Right now, I'm talking about the Euclidean space in three dimensions that can be expressed at a point in a three-dimensional Euclidean space is completely described by a vector as a linear combination of three linear independent vectors called unit basis vectors of the Cartesian coordinate system, and we need three real numbers to represent a vector. This representation depends on the choice of the origin of the system, and if we translate this origin from somewhere to another place whose position vector relative to the original origin is a, then an arbitrary vector x can be represented by another vector x prime, provided that we have the relation x equals x prime plus a. Because of this relation, I can determine the x prime vector to be x minus a. Therefore, Cartesian components relative to the new origin should be expressed in terms of x1 minus a1, x2 minus a2, and x3 minus a3. Okay. This translation is allowed because the Euclidean space is homogeneous and isotropic. So, whatever point you may bring in, we can translate the system, the origin of a system to another to represent the same vector in terms of the different coordinate system. This method is quite useful to find completing the square. This is closely related to the translation. First, we solved a very simple quadratic equation, that is x squared equals 0. Everybody must know that the solution is uniquely defined by x equals 0. The reason is that a real number is either 0 or not. If it is not the case, it is a positive or negative. Any positive or negative number square must be positive definite. Therefore, if x squared equals 0, the only choice is that x is 0. This is true even if we extend the set of numbers from the real number to complex number. Why don't we introduce a complex number whose real part is x and the imaginary part is y? If we square this complex number and expand this using the fact that I squared equals minus 1, then we arrive at the point the real part is x squared minus y squared and imaginary part is 2xyi. Now we arrive at the point that if it is a 0, then the real part, both the real part and the imaginary part must be 0. Real part equals 0 only if x equals plus minus y. Imaginary part is 0 if x equals 0 or y equals 0. Because x equals, if x equals 0, then if I substitute this one here, I find that both x and y are 0. If y equals 0, using the same method, I arrive at the same result. So, in complex number, square of a complex number is 0 if and only if complex number itself is 0 plus I0, that is a 0. Next, we solve another quadratic equation, x squared equals 1. We now move this one to the left-hand side and we factorize this. The product of two real number equals 0, then either one is a 0. The answer is either plus 1 or minus 1. Another problem, x squared minus 1, can be solved by moving this minus 1 to the left-hand side. We can now factorize this one by rewriting this plus 1 with a minus minus 1. Because I is a pure imaginary number that satisfies the square root of minus 1, I squared is minus 1. Therefore, this one can be expressed as I squared. That is x plus iy, I, and x minus y, I. Because the product is 0, and we know the complex number square is 0, any complex number, product of complex number is a 0 when either one is 0. Therefore, this x is either plus I or minus I. Now, we find a multiplicative inverse of a complex number z. C has one-to-one correspondence with the two-dimensional Euclidean space because the real part x and imaginary part y can be a Cartesian coordinates of the two-dimensional Euclidean space. So real part z is x, real part of z is y, and these two can be identified as the two Cartesian coordinates of the two-dimensional Euclidean space. The product z1 plus times z2 can be computed by expanding this complex number in terms of real and imaginary part, and the product shows that real part of the product is this, and imaginary part of this that carries us only a single I is this. The negative sign comes from the fact that I squared equals minus 1. Why don't we next consider complex conjugate of a complex number z is identical to z except that the sign of the imaginary part is negative. So opposite. So if I multiply these two mutually complex conjugate number, then the result is positive definite square of the real part plus the square of the imaginary part. So we define the square root of this to be the magnitude or modulus of a complex number. We can make use of the polar coordinates r and theta to represent the complex number by employing Euler's formula. That is, exponential I theta is cosine theta plus I sine theta. We know The real part is our cosine, and imaginary part is our sine. So using this, we can reproduce the modulus of this complex number r is absolute value of z and the square root of x squared plus y squared. Next, we find a multiplicative inverse of z that is not equal to 0 is, we begin with 1 over z, we multiply 1, that is a z star, divided by z star. Then the denominator combines into a single value that is the absolute value of z squared. That is a square of x and y squared sum. Now we find that we have a negative sign relative to the x plus iy that is the original complex number z. Next we solve the equation. Two complex numbers are the same. What is the condition? We expressed each complex number in terms of the real part and imaginary part, then subtract. Then, if they are the same, that means subtraction must give a 0. If it is a 0, then both real and imaginary parts must be the same. However, if we make use of the polar coordinates, r and theta is a little different. Let's see. The two numbers are the same. This complex origin, radius r1, r2. These two points are the same only if the radius are the same. Okay, radius, two radii are the same. Then they must meet together. Okay, so this theta angle between these two must vanish. However, it is true for any 2 pi times integer will be allowed because it returns to the same point. As a result, the difference of the two angles doesn't have to be 0, but it is a multiple, any kind of multiples of 2 pi. As a result, just 1 is a 1 plus I0 that can be expressed in multiple ways. That is exponential 2n pi I, because this one is always 1 and this one is always a 0. As a result, if I have a polar coordinate representation of two complex numbers, radii, this modulus must be the same, but the angle doesn't have to be the same, except that the difference is 2 pi times any integer. Using this result, we can solve the equation for z to the n equals something. But before we study that, what is the z to the n in polar coordinates? Square, radius squared, and angle 2 times angle. And this is true because of the law of exponent applies also to the exponential function. So you're familiar with this kind of derivation. So let me pass. This method, this expression is true for any n. So you can prove this using mathematical induction. Next, we consider the case z to the n is a constant complex number. This constant complex number can be expressed as polar coordinates, radius multiplied by e to the I theta 0. Okay, so we introduced z equals r e to the I theta. What about z to the n? Radius to the nth power, and exponential I theta's nth power is just extending the angle by n theta. By the way, this we are looking for the solution for this equation, and the polar coordinate representation of a constant complex number is r0 exponential I theta 0. We have to add this to include the most general case because the 2 pi k it doesn't change anything about the z0. However, if I find the equate this radius r to the nth is r0, so radius is the nth root of r0, and n theta, this angle, should be the same as the theta 0 plus the 2k pi. Here we have theta. There are many thetas. Because we divide this both sides by n, this k returns to the same value if I shift k by plus n. So there are n distinguishable angles that result in the same result for the z0 for a given z. So there are n such solutions for the equation z to the n equals to z0. Now we solve the quadratic equation we are very familiar with. So alpha equals non-zero only if in the case it is the square term survives to make a quadratic equation, not a linear equation. We'd like to transform this equation by completing the square to simplify this as this kind of form. So what should I do? I first divide because there is a no over factor and this alpha is not zero. I divide both sides by a. And I assume this expression can be reduced into this kind of form. The reason why I have introduced a factor of 2 is to simplify this. So I first divide both sides by a. Is 0. So would like to reproduce this form. That means 2 beta equals b over a. So beta equals to b over 2a, and gamma equals c over a. Now, we'd like to remove the linear term by translating the origin. So it can be made by introducing a new variable y in such a manner. Why? X squared plus 2 beta x comes from this expansion of the x plus beta squared. Now, this one and this one match together. If I want to simplify this as completing the square, what I need to do is replace this one with this one subtracted by beta squared. Now, replace this one with y. So y equals x plus beta. In that case, this expression becomes y squared minus beta squared minus gamma equals 0. So y equals x plus beta, and then this beta squared minus gamma equals delta squared. This is to reduce this equation into very simple form. Because the equation reduces into this form equals 0, the solution of y is trivial. And because of this and this relation, well, is it y equals x plus beta? And delta can be found by square root of beta squared minus gamma. And beta and gamma are given in here. Substituting those values to find that this one that we are very familiar with. Okay, square root of a squared is identical to the absolute value of a when a is a real number. It is trivial to show that y equals plus minus delta. We have already shown, and we have a definition y equals x plus beta Therefore, the solution of x is minus beta plus minus delta, and plus minus delta is available in here. So whether a is a positive or negative, plus minus something. So we can unify these two terms to find that the solution of x of the quadratic equation can be found from this simple factorized formula. As a result, we find the final solution. However, we can't check the sign of the argument of the square root if we define this one by b squared minus 4ac by the discriminant. If the discriminant is a positive, then the square root term is a real number. If it is negative, then the square root term is a pure imaginary number. So we can choose the representation of this or this. Actually, they are identical to each other. The convenient choice for the negative discriminant is this one. And if discriminant is equals to 0, then there is only a single solution. We call it double root. That's it for today. Thank you.